Welcome back. This is part 2 of our lecture for subject contrast, chapter 12. We've talked a lot about attenuation and how that makes up your subject contrast. Let's talk about transmission as well. If you think back to the flow chart at the start of these PowerPoints, your X-ray can either transmit or attenuate. Transmission, no interaction at all, just going straight through the part to your detector or your image receptor. So what affects the odds of beam transmission? Primarily, it's the energy of the X-ray beam. Penetrating energy, the penetrability, also called the X-ray quality, and that is controlled by you, the technologist, when you set the KVP. With a higher KVP, you are increasing the overall energy level of the X-ray beam because we will have more photons with higher energy levels. Remember your beam spectrum. You make your exposure. Not all the X-rays have the same energy. But if you increase the KVP, you're giving the overall beam more energy. So we're increasing the chances that the photons are going to pass through your patient and reach the image receptor without interacting with any atoms. No electron strikes, no scatter. It's just going straight through. And if we do that, we're going to reduce the subject contrast in the remnant beam because we've increased transmission. Those photons are going to penetrate the object, the transmitting photons. They're going to penetrate the object. They're not going to get absorbed. They're going to go straight through and increase the signal to the detector. Increased signal means more shades of gray. More shades of gray, long grayscale. And the opposite, long grayscale, low contrast. Think about an AP foot. You're going to take an X-ray of an AP foot, 55 kVp. In DR, it's still relatively low, but when you do that, you're going to have a good amount of photoelectric interactions in the bone and in the soft tissue. And you're going to have a nice bright bone in the foot. You're going to have gray soft tissue, and you're going to have that sea of black around the foot where you're just exposed to the air. Your standard run-of-the-mill AP foot, relatively high contrast, big distinctions between the visual bony anatomy and the soft tissue. Now, if we increase the KVP, we're giving the overall X-ray beam more energy. We're increasing the chances that those X-rays are going to pass through without interaction. They're going to reach your detector. They're going to be logged as an X-ray strike. And you add all of that additional signal, and you're going to get more shades of gray because every little strike is a little speck on your image. You add them all up. More specks, everything gets a little grayer. And you can take an X-ray of an AP foot with a high KVP, but you would expect the bony anatomy to be closer in shade to the soft tissue because there's There's more transmission through the bone. There's more transmission through the soft tissue. Underneath that foot, the detector, it's going to register more hits, so everything gets a little more gray. We increase the grayscale, we've reduced the contrast. We've reduced the subject contrast. Because the remnant beam no longer has big gaps where the bone is. Now, those gaps where the bone is have transmission occurring as well, in addition to the scatter. And sometimes we want a low contrast picture, but it's not always ideal for the anatomy that we're x-raying. So not as useful to the radiologist when they're looking for fractures in the foot. You don't need to see super distinct shades of gray from the soft tissue. You want to look at the bone when you're x-raying a foot. So higher KVP, not always ideal. You will reduce the subject contrast when you increase the KVP. Here's another example of KVP and its effect on penetrability. I will again note the illustration. Wavy lines indicate photons. Lower energy is less tightly coiled than the high energy photons. So on the left-hand side, you're x-raying two abdomens, low energy KVP beam, more attenuation is happening because fewer are just being transmitted. You still have some transmission, you always still have transmission, along with your absorption and your scattering. But with a low energy beam, you're not going to have as much direct transmission. On the right-hand side, high energy KVP beam, you've got more energy on those photons, more energy to penetrate, in addition to the absorption and scattering that's happening. Keep that in mind when you're setting your console. You are affecting all of that. Your exam protocols and your system protocols are set up with optimal KVP in mind. Not always, in every case, is what you want to use. Sometimes they're out of date. But it does affect the ratio of attenuation versus transmission. You don't want to go overboard with KVP when you want to see bony anatomy. So for extremities, that's another reason why we tend to use less KVP, along with the part thickness. It's just what's going to give us the contrast that the radiologist needs to assess injury. Okay, so now we're going to get into what typically is one of the more complicated parts of this course. We're going to look at probability, or if you want to think in terms of gambling, what are the odds of something happening? We need to look at our probabilities for attenuation. And it matters what energy level we're using, and it matters what type of tissue X-rays are interacting with. I'm going to go through in broad strokes what you should get from these charts, and then we will look at some probability charts from other textbooks, and then the chart included in our digital age textbook. I've got them all included. They show relatively the same information, just different perspectives on it. Okay, first up, photoelectric effect. We're talking absorption here. Photoelectric effects, you will remember, involves an X-ray striking an inner shell electron of an atom, giving all of its energy to that electron and ceasing to exist. It's given up all of its energy, giving all of that energy to the electron, knocks it out of orbit. It becomes a photoelectron. So the absorption is when that photon ceases to exist. All right, now that we know that, what are the odds of having a photoelectric reaction? Well, it depends in great degree on the energy of the photon. The more you raise the kVp, the more you dial down the odds of having photoelectric absorption. So energy is a big, big factor here. But so is the atomic number of the tissue. Diving just a little bit into the physics here, incident X-ray photon energy, so the X-ray that's coming in, it has to have enough energy to meet or exceed the energy that's holding that electron in orbit around the nucleus of an atom. If not, it's not going to have a photoelectric interaction. You have to have enough energy to dislodge the electron that's in orbit. And not every X-ray is going to meet that criteria. So your book has a little analogy that I like. The short answer here, you'll get into calculating binding energies in the fall. But for now, it's enough for you to know that the inner shell electrons are really choosy about which X-rays they'll interact with. On the Compton side of things, we have probability of Compton scatter only slightly affected by kVp. Photoelectric, it's a huge effect, whatever kVp you are setting. Compton doesn't really care too much about kVp. That's because the Compton interactions involve outer shell electrons. So your initial photon, just summarizing the Compton interaction for you, initial photon comes along, interacts with an outer shell electron, gives up part of its energy, and knocks that electron away. That recoil or Compton electron goes off, does its own thing. The initial X-ray is not absorbed. It's just banked off a little particle, and it goes off in a new direction with less energy than it started. It becomes a Compton scatter photon at that point. And these outer shell electrons are not as choosy about interacting with X-rays like the inner shell is. The end result of that is the odds of Compton scatter in soft tissue and in bone are about the same. Now, the real confusing part about all of this is what I've got underlined here. If you keep increasing your kVp, you will slightly reduce the number of Compton interactions. That's simply because when you increase your KVP, you are increasing the odds of no interaction at all, of transmission. So if I crank up the KVP, I'm betting that it's going to transmit before it's going to scatter. So where this gets really confusing is our rule of thumb of high KVP, more scatter. We've talked about that already. And a lot of techs will tell you, oh, don't make the KVP too high, you're just going to get more scatter. And I'm telling you that when you have more KVP, you're actually reducing the number of Compton scatter interactions. How does that square? How is it possible to have fewer Compton interactions and yet I get more scatter on my image when I'm using high KVP? We will make sense of that. We need to start looking over these charts, and it's easy to get confused by some of the graphs in this chapter. You have to look closely at what each axis on the graph represents. Just summarizing, figures 12.5 and 12.6 in your book. As you increase your KVP, you are decreasing both your Compton and your photoelectric interactions overall. Decreasing interactions means more transmission. So that's takeaway number one. As you increase your KVP, your odds of interacting at all are going to decrease. More chance that you're going to transmit. So that's number one. Number two, as you increase your KVP, the interactions that are left over at high KVP, predominantly Compton. We'll get into that a little bit more as we start looking at these illustrations. First up, a probability graph from a textbook that you do not have, but very similar to the chart on figure 12.5. Figure 12.5 shows photoelectric and Compton for soft tissue. Here, we've stripped Compton out of the equation. We're just looking at photoelectric probability. And instead of just looking at soft tissue, we have a dash green line indicating soft tissue and a blue line indicating bone. Let's look at the axes first. Along the horizontal x-axis is X-ray energy, here in KeV, which we have previously said you can think along the lines of KVP. KeV is the more precise energy level of any single photon in your beam. On the y-axis, it's relative probability of interaction, and it's in a kind of logarithmic scale that we're not going to get into. But in general, the closer that y-axis is to 0, means less odds. Okay, so let's take a look at the soft tissue curve. We're going to start close to both axes here. This is a really low energy level, 20 keV. With a low energy level, very high probability that you're going to have a photoelectric absorption. It's up here. And that makes sense. At low kVp, at low energy levels, you're more likely going to have absorption. We see that all the time in a regular X-ray. If you're doing a hand, use lower kVp than you do for most of the rest of the body. And we get more absorption in the bone and the soft tissue. We go, think back to our choosy inner shell electrons. In the body, these low energy photons are going to match up very nicely with how picky those inner shell electrons are. So at low energy levels, you're going to have a lot more absorption. As you increase your energy, the probability of absorption decreases. And the higher energy photon is more likely to pass through the tissue. So we're just looking at the soft tissue line right now. If you increase your energy level to 40 versus 20, it's about half the distance. So we've decreased the odds of photoelectric absorption, but there's still a whole lot there. Keep going though, and it starts to drop precipitously. So by the time you get around 60 keV in soft tissue, we have pretty much eliminated absorption as an interaction. Beyond 60 or so, it's not going to be absorbed in the soft tissue. It's going to transmit. Still looking at the soft tissue line. Look how close to zero my probability of photoelectric absorption is at this energy level. So if I keep cranking it up to 80, soft tissue is not going to absorb anything. It's just going to transmit. This is kind of where we are for soft tissue of a hand, by the way. Okay, so that's the soft tissue graph. Let's look at the bone line. Blue slope. This is bone in your body in terms of the probability of a photoelectric interaction. At low energy levels, say back at 20, sky high. Really big odds that at low energy levels, the bone is going to absorb the photon. You're going to have that photoelectric interaction. As you increase odds of probability for photoelectric reaction, they start to drop off. And so on. As you increase the energy, you are reducing the probability on this axis that you're going to have absorption. So it caps out above 100 keV. So at 120, we've pretty much eliminated photoelectric absorption in the bone. We're just transmitting through it. Soft tissue fell off way back here. Bone is still going to be really good at absorbing X-rays, even at these high energy levels. And that tracks with what we see on our pictures every day. Bone shows up very bright on your image because X-rays get attenuated very well in bone. They get absorbed very well. Even at high energy levels, the bones stand out visually because even at those higher energy levels, you're still having more absorption going on because of this probability curve. So we're not talking about Compton at all. We're just looking at photoelectric. And the key takeaway here is as I increase my KVP, I am decreasing the odds of photoelectric absorption. Instead, if they're not getting absorbed, they must be transmitted. Because we're not talking about Compton at all. So it's either being absorbed or it's being transmitted. For whatever energy level and whatever tissue type, if it's above the curve, it's not going to be absorbed. If it's below the curve, it's going to be absorbed. Okay, that's the photoelectric side. Fairly easy to grasp. Lots of absorption at low energy levels. The more you increase it, less chance of absorption. That is true for soft tissue and for bone. But bone is so much more likely to absorb than soft tissue. And we talked about that with our atomic number probability. You cube the atomic number, that's how much more likely a photoelectric reaction is in the bone than soft tissue. All right. Next up, the probability of Compton scatter. Now this is interesting because it's pretty similar for bone and soft tissue. There are subtle distinctions, but they're not too far apart from each other in terms of those slopes. Going back to photoelectric, pretty broad gap here between odds of soft tissue absorption and bone absorption. Compton, they're pretty even. So just looking at this chart, it tells you the probability of a Compton interaction is about the same for the bone and for the soft tissue. But it's not a straight line. It is a slope. And the probability of having a Compton scatter interaction decreases as your energy level increases. So we got soft tissue in the green line, we got bone on the blue line. At a low energy level, you have a good chance of scattering, just like you have a good chance of absorption. That's fairly similar for bone and soft tissue. So bony tissue is going to have slightly higher odds of Compton scatter, but not much more than the odds in soft tissue. As I increase my energy level, that curve starts to level out. But it does keep decreasing. It's going to be a long way to get to zero, because even at really high KVP, 140, you still have a probability of Compton scatter. But it does continue to slope down and decrease. If we keep increasing past the diagnostic levels that our machines are capable of, it's going to get a little more closer to zero. So we're not talking about absorption here. We're just talking about, is it going to scatter or is it going to transmit? And at higher energy levels, we're decreasing the odds of Compton slightly. And if we're decreasing the odds of Compton, then we have to be increasing the odds of transmission. Just a little side note that this chart, since it's from a different textbook, it suggests a steeper decline in Compton than the chart in figure 12.5, but both of them do show a gradual decrease in Compton probability as you increase your energy level. So we get two charts, photoelectric probability and Compton probability. Now we're just going to put them together. This looks more complicated than it is. But all this is the last two graphs put in one picture. Because in our exposure, we're dealing with all this at the same time. We're dealing with the odds of photoelectric, the odds of Compton, the odds of transmission. So we're smashing them all together here. Dashed line indicates soft tissue, solid line indicating bone. So your takeaways here. For both Compton and photoelectric, the probability of interaction drops as your KVP increases. That's all consistent with what we've covered for these graphs individually. When you put them together, you can see that at higher energy levels, photoelectric has dropped off completely. Let's back up. Let's look at an exposure made at 50 keV. So 50 kVp, your energy level of your photons, if you got a 50 keV photon, it has a good chance of being absorbed. That is here in the soft tissue. It's pretty low. It's not zero. It's pretty low. Now we draw a line up from 50 in bone, and it's a lot higher. So 50 kVp photon has better chance of being absorbed in the bone than in soft tissue. And that makes sense. Compton, they're pretty equal. You're going to have a decent amount of Compton scatter in the soft tissue and in the bone. So that's low energy level. Let's increase it. Let's bump it up to 100 keV. So maybe something that involves contrast. At 100, photoelectric interactions have totally dropped off. We've given the X-ray photons so much energy that the inner shell electrons, they're like, nah, not for me. They're too choosy. They don't want those high energy photons. They want the low energy ones. It's too much for them to interact with. So you end up with no absorption at those high energy levels. You end up with transmission, or you end up with Compton scatter. So at high KVP, Compton is the dominant or only interaction left. Photoelectric absorption totally dropped off. So you're left with, it's either going to scatter or it's going to transmit. Photoelectric absorption has fallen away. So that's why you end up with more scatter at high KVP. Because even if you have cranked up the KVP and you have slightly reduced the odds of Compton interactions, because at those high energy levels, you've eliminated photoelectric from happening at all. What's left over is scatter. It's either going to transmit or it's going to be scatter. So when you use high KVP levels, you end up with more scatter on your image just because that's the dominant interaction that's left. And that can trip people up because you see that on an exam question. If I increase my KVP, what does that do to my probabilities? Well, it decreases the probability of photoelectric. It also very slightly decreases the probability of Compton. That doesn't mean that it drops the number of scatter photons that are hitting your detector. It's just that what's left over, it's not going to be absorbed. It's either going to scatter or it's going to transmit. So at high KVP levels, you end up with more scatter on your image because Compton becomes the dominant interaction. All right. So this is the graph that's in your textbook. And it's very similar in terms of the slope. We're just looking at soft tissue here. It shows the average atomic number of your soft tissue and the relative number of interactions at each energy level. Notice that that photoelectric curve drops off near 60 kVp. Compton, though, for all tissue, not just bone, and soft tissue as well, Compton's in this range here. So at any energy level, you're going to have a fair amount of scatter. Notice this very gentle slope, but it is decreasing. So at 80 kVp, I still have Compton scatter occurring. At 100 kVp, I don't have any more photoelectric interactions in the soft tissue. I still have scatter, but I have fewer scatter interactions at 100 than I do over 80. So that slope continues to decrease as I increase my KVP because I'm transmitting more than I'm scattering. So text graph showing the relative predominance of photoelectric and Compton interactions within soft tissue at increasing levels of KVP. All interactions decrease in number at higher energies, so that's less photoelectric, less Compton. However, photoelectrics drop precipitously to 0, leaving Compton behind as the prominent interaction at higher KVP levels. So when your old school tech says you get more scatter, the more you increase your KVP, this is why. Even though on an atomic level, you're having fewer scatter interactions at higher KVP. It's just that we've eliminated the absorption, so all that's left is scatter. So you're going to see a bigger effect on your image from all of that leftover scatter. I know, it's weird. The last thing we need to talk about here is contrast media. Contrast agents can introduce subject contrast in tissues that would otherwise be indistinguishable. You know, we have positive contrast agents and negative contrast agents. The reason why we use those is we want to image anatomy that otherwise you could not see distinctly. So positive contrast uses elements and molecules with higher atomic numbers. We know that atomic number is a huge effect on the probability of photoelectric interaction. So 12.6, figure 12.6, which I have on the next slide here, is photoelectric interactions for soft tissue, for bone, and for iodine, one of our positive media. Note that iodine has a Z number of 53, much higher than the average Z number of bone. So at any energy level, a lot more photoelectric interactions happening versus the soft tissue and the bone. Barium has a higher atomic number than iodine does, 56. So the slope would be pretty similar. We can use negative contrast agents as well. That's air, carbon dioxide. They also induce subject contrast by increasing transmission instead of absorption. So the high atomic numbers in positive contrast media, they cause a huge surge in photoelectric absorption. That's why contrast media shows up even brighter than the bone when you use it on radiograph or in fluoro. So this is another combo chart, photoelectric and Compton displayed at kVp ranging from 0 to over 140. So let's look at back here at 40 kVp, pretty good odds of photoelectric absorption in soft tissue. But we've gone from 0.1 to, let's say, 50. So about 500 times more likely that your X-ray would be absorbed in the bone rather than the soft tissue. But even greater odds that the iodine is going to absorb rather than the bone. The high atomic number in the iodine is even more an attractive target because it's got more electrons to play with. And it's just better at absorbing because of that higher atomic number. You got a high atomic number, really likely to have photoelectric absorption. Compton, it's about the same throughout. And as we increase our energy level, we've gone up to 120 here. We've eliminated photoelectric absorption in the soft tissue. We've knocked out most of them in bone. We still have a small percentage that are being absorbed in the bone. But look at the huge gulf here between where the bone is absorbing and where the iodine is absorbing. Even at really high kVp levels, the positive contrast media is super efficient at inducing the photoelectric effect. It's going to be absorbing X-rays like crazy. So at really high kVp levels, you're going to see that contrast media. And when we do studies involving the GI tract, stomach, barium enema, we use like about 120 kVp. And we still see super bright outline of the anatomy because the contrast media is that good at absorbing, even at the really high kVp levels. So we can cut the dose to the rest of the patient and still have that photoelectric absorption going on. Okay, let's finish things up. As we increase our kVp, what does that do to the probability of photoelectric absorption? It decreases it. More kVp, less absorption. If I increase my kVp, my odds of Compton interactions slightly decrease. I keep increasing my kVp, photoelectric drops off, and the remaining interactions are mostly Compton scatter. Remember that even at very high kVp levels, I'm still going to have Compton happening, even though absorption has dropped off. So what's left over is scatter. That gives me an increased percentage of scatter, decreased percentage of absorption. Compton scatter typically predominates within the energy ranges we use for diagnostic images. Photoelectric interactions predominate when you've got low energy ranges, so techniques of 40 to 70 kVp. Extremities, there's more likely to be a fracture in bony anatomy. For extremities, we want to do lower energy ranges to enhance the chances of photoelectric absorption. We also have photoelectric dominating in elements with high atomic numbers, and that includes a prosthesis. So if you know your patient has hardware in there, you can increase the kVp. You shouldn't need to, but you can. Definitely going to need to increase the mass because that hardware is denser than the bony tissue, than the soft tissue. It also has a higher atomic number, so it's going to attenuate so much more of the beam. And that may leave you with less signal getting to your detector. So you may end up with quantum model if your patient has a lot of hardware. And then here's a little chart, up and down arrows for different attenuation factors. This is not in your textbook, but most of this is common sense. Tissue thickness, more attenuation, more absorption, less transmission. Less thickness, less attenuation, less absorption, more transmission. So you can look at each of these factors and think, okay, it's overall attenuation, including absorption and scatter. It's going to go up or down. Same with absorption, same with transmission. Scatter, you got to remember that that probability is pretty even throughout the energy ranges we use. The final factor here, X-ray beam quality, that's your kVp, your energy level. Increasing beam quality means more kVp. What does that do to absorption and transmission? What if I lower the kVp? What is that going to do? And that's it. This is some of the trickiest stuff in this course. So if you can get through this, the rest of it should be a breeze for you. Thanks, everybody.